Charlotte Green, and today we will be talking about non-Newtonian fluids. Now, I'm sure there's been a time in your life when you've held oobleck, a funny liquid that's hard when you squeeze it, yet soft when you let it flow through your fingers. Well, there's a reason behind that, and it's called non-Newtonian motion. A non-Newtonian fluid is simply a fluid that doesn't follow Isaac Newton's law of viscosity, which states the ratio of shear stress to shear rate is constant. Now, I know that sounds like a lot of big, fancy words, but essentially all it means is that the viscosity of a non-Newtonian fluid changes with pressure. An example of a Newtonian fluid, such as syrup, does not change viscosity when pressure changes with it. Oobleck isn't the only kind of non-Newtonian fluid. There are tons. There's ketchup, whipped cream, silly putty, shampoo, and toothpaste. There are so many different kinds, but this project will focus on dilatant fluids, which are fluids that become thicker when larger pressures are applied to them. So why exactly does oobleck behave the way it does? Well, it all has to do with what it's made of. Okay, so as you can see from looking at this graph here, you have on your x-axis the shear rate, which is the same thing as the pressure being applied. On the y-axis you have the shear stress, which means viscosity. Let's look at this Newtonian line for a minute. As you can see, the ratio of the x and the y-axis is a straight line, meaning that the ratio of shear rate to shear stress, or pressure to viscosity, is constant. It's a 1-to-1 ratio, and will always remain that way, meaning the viscosity will not change as pressure changes. Let's look at our dilatant line, for example. That is a dilatant fluid. Oobleck is an example of a dilatant fluid. Oobleck's viscosity changes exponentially with pressure. So as the shear rate goes up slightly, the shear stress goes up extremely. This means that the viscosity becomes very high as pressure increases, meaning, of course, dilatant fluids become thicker with pressure. If you look at the pseudoplastic line, that is an example of a non-Newtonian fluid, but it does the opposite effect of a dilatant fluid. A pseudoplastic fluid, as you can tell from the graph, decreases in viscosity as shear rate increases. So, as the pressure increases, the liquid actually becomes thinner. An example of a non-Newtonian fluid that behaves this way is ketchup. As you shake the bottle, the ketchup becomes more liquid. Oobleck is made of cornstarch and water. The chemical formula for cornstarch is C27H48O20, which is a huge and complex molecule. It is also a polar molecule, meaning it has rather strong intermolecular forces that make the molecules want to stick together. Suppose you had a very dilute solution of cornstarch and water. In this case, the spacing between the starch grains is large. The grains can flow around each other without hitting each other, and the suspension behaves just like water. As you increase the amount of starch, the spacing between each grain decreases, until at some point, the spacing between the grains becomes smaller than the size of the grains themselves. At this point, when you try to apply a large force, the starch grains bump into each other and lock together to form a framework. If you apply a small amount of force to the fluid, the grains move slowly, and this gives time for them to slide around each other. Non-Newtonian fluids hold potential for use in future technologies. In recent years, scientists have been trying to use non-Newtonian fluids as a way to make special body armor that becomes fluid when moving, yet strong when it gets a quick impact, such as a bullet. It would allow people wearing it to be flexible and still survive large impacts. Or you could use it to design a shoe that is soft and flexible for walking, but provides large amounts of support for runners. I hope you enjoyed this brief intro into the world of non-Newtonian fluids. So get out there and try it for yourself. Break some laws. Newton's laws, that is.